This is prerequisite lesson number 2 for this collection of Algebra 2 lessons, which is all about roots, imaginary numbers, and complex numbers. You remember from Algebra 1 that you can multiply roots together. Here we see that root 4 times root 9 is equal to root 36. Root 4 is equal to 2, root 9 is equal to 3, and root 36 is equal to 6. 2 times 3 is 6. The reverse is also true. You can also break up roots into factors. So root 20 is equal to root 4 times root 5. Now, since root 4 is equal to 2, this can be simplified to 2 times root 5 or 2 root 5. 2 root 5 is a simplified form of root 20. You can check this with a calculator. Enter root 20 on the calculator, and then enter 2 times root 5, and you'll see that they're the same thing. Can root 18 be simplified? Yes, you can break it up into root 9 times root 2. Root 9 would be 3, and root 2 doesn't simplify, but it all simplifies to 3 root 2. Now, although you could break up root 18 into root 6 times 3, you wouldn't want to do that because neither one of those are perfect squares, and that's not going to help you to simplify the root. So basically, it's important to have a perfect square factor. It's critical, in fact. Root 35 is not going to simplify. If you list out all the factors of 35, none of those factors are perfect squares. So root 35 is fully simplified. Can't be simplified any further. So it is critically important that you know all your perfect squares. So I'm going to ask you now to pause the video and list the perfect squares less than 300. They are 1, 4, 9, 16, 25, 36, 49, 64, 9 times 9 is 81, 10 times 10 is 100, 11 times 11 is 121, 12 times 12, 13 times 13, 14 times 14, 15 times 15, this is 16 times 16, and 17 times 17. That should be good enough to help you simplify any radicals that you'd see on a test. All right, so let's do some guided practice. What you're looking for here are perfect square factors. So what's a perfect square factor of 50? That's right, 25. 25 simplifies to 5, so this whole root simplifies to 5 root 2. How about 27? Are there any perfect square factors of 27? That's right, 9. 9 will come out as 3, so you'll end up with 3 root 3. If this is difficult for you on a test, you might want to write the perfect squares down the side of your test. 1, 4, 9, 16, 25, 36, on up to 100, say, or maybe even beyond, just to give you an idea of what the perfect squares are. Can you think of a perfect square factor of 98? This is kind of a hard one. If you guessed 49, you are correct. 49 goes into 98 twice. Root 49, of course, is 7, so 7 root 2 is a simplified form of root 98. Root 12 would be root 4 times 3, and the 4 comes out as a 2. 2 root 3. Perfect square factor of 45? 9. So that simplifies to 3 root 5. Perfect square factor of 28? 4. So that would be 2 root 7. Sometimes students will simplify a root, but they'll stop like halfway through. Like, for instance, root 72, they'll break it up into 9 times 8, and they'll take the 9 out, and they'll get 3 root 8, and they'll just write that in the answer column, 3 root 8. But they didn't realize that they left another perfect square in there. 8 is 4 times 2, and 4 is a perfect square. So when you simplify radicals, you got to make sure you take out all the perfect square factors, not just one of them or some of them. You got to take them all out. Now, if this person had realized that 9 times 8, yeah, 9 is a perfect square, but a larger perfect square would have been 36. 36 times 2 is 72. So it's hard to know your factors up to 36, but whatever you do, just don't stop part way through simplifying a radical. Make sure you've checked all the remaining factors inside the radical and you removed all the perfect square factors. Okay, now try these. Root 32 would be 16 times 2, so the 16 comes out as 4 root 2. 200 can be broken down into 100 times 2, so that's 10 root 2. Root 80 is a tough one. Yeah, 4 goes in, but can you think of something larger? If you take a 4 out, you'll leave a 20 behind, and there's another 4 in there, which means you could have actually taken a 16 out. That's 4 root 5. Root 30 has no perfect square factors, so it's already fully simplified. Can you think of a perfect square factor of 48? 4 goes in, but I think 16 also goes in 3 times, so that'll be 4 root 3. And 60, I think a 4 goes into 60. I think that's probably the largest perfect square factor. You can take the 4 out, so that's going to be negative 5 times 2, which is negative 10 root 15, and 15 has no perfect square factors. So you see, simplifying radicals is much like reducing fractions. You got to make sure that you reduce it or simplify it all the way. What goes into 54? That's a perfect square. I believe 9 does. So when you take the 9 out, you get 3. But there's already a 5 out there, so 5 times 3 will give you 15 root 6. With 48, you can take out a 16, so that'll be 4. There's already a negative 7 out there, so negative 28 root 3. Remember, you can pause this at any time and work on these on your own if you want. 42, 4 doesn't go in, 9 doesn't go in, 16 doesn't go in. I don't think there are any perfect square factors of 42, so it's already fully simplified. 40, we know 4 goes in, 9 doesn't go in, 16 doesn't go in. I don't think we can take anything other than a 4 out. So it'll be negative 6 root 10. A lot of times people will forget to root it when they take it out, and they'll get negative 12 root 10 because they think it's negative 3 times 4. But remember, when you take that 4 out, you got to square root it. Root 180. You could take a 9 out, it'd be 9 times 20, but then you think 20, there's a 4 in there. So you can actually take out 36. 4 times 9 is 36, which means you can take a 36 out of there, giving you 6 root 5. 4 root negative 9. This is not a real number. If you wanted to simplify it to be an imaginary number, we're going to talk about that in a little bit, how to do that. Okay, there are 3 rules for simplifying radicals. Rule number 1 we're already familiar with. Leave no perfect square factors in a radical. We've already seen how to simplify root 50 down to 5 root 2. Rule number 2, leave no fractions or decimals in a radical. So if you have root 3/4, you can break that up into the square root of 3 over the square root of 4. Square root of 4 is rational, that's 2. Square root of 3 is irrational, but there's nothing you can do with it, so you just leave it as root 3 over 2. Now, you can leave a radical in a fraction, so it's okay to leave root 3 in the fraction root 3 over 2, but you can't leave a fraction in a radical. Finally, rule number 3, leave no radicals in the denominator. Often on tests, they'll say rationalize the denominator. I'm going to show you what that means. Right now, we're breaking rule number 2. You can't have any fractions in a radical. So we break it up. Root 4 is going to be 2. Now you have 2 divided by root 3. Your denominator is irrational. We need to rationalize that denominator. We need to get the root 3 out of the denominator because you can't have any radicals in the denominator. So to do that, I'm going to multiply by root 3 over root 3. This is allowed because root 3 over root 3 is 1. And when you multiply stuff by 1, it doesn't change. So you get 2 root 3 over 3. You no longer have a radical in the denominator, and that's fully simplified. All right, now try these. See in problem number 1, you're breaking rule number 2, no fractions in a radical. So you break it up, simplifies to root 5 over 3. In problem number 2, same thing, can't have fractions in a radical. We simplify the denominator because there's a 4 factor that goes into 8. We take that out. We get 2 root 2 in the denominator. Now you're breaking rule number 3. Can't have any radicals in the denominator. So you multiply by root 2 over root 2. That gives you root 6 over 4. Problem number 3, we're actually breaking rule number 2 here. You can't have any decimals or fractions in a radical, but I never showed you how to deal with a decimal. All you do is you change that decimal to a fraction. So root 7 over root 10. Multiply by root 10 over 10 to rationalize the denominator. You get root 70 over 10. Finally, number 4, change mixed numbers to improper and simplify the radical. And you end up with 2 root 15 over 5. Okay, now we're ready to talk about imaginary numbers. What do you do with the square root of a negative number? Well, we're going to define the square root of negative 1 as I. So what do you do with the square root of negative 4? Well, you can break it up into the square root of negative 1 times 4. You can split that root into two different roots. And we know the square root of negative 1 is I, and the square root of 4 is 2, so we're going to call this 2I. The next one, square root of negative 25. You can't take the square root of a negative number unless we break it up into root negative 1 times 25. And that's going to simplify to 5I. Pretty obvious now. That's going to be, square root of 81 is 9, so it's going to be 9I. This is the opposite of the square root of negative 64. Now, that negative outside is going to be unaffected by the negative inside. So we're just going to keep it and follow it around. It's going to end up being negative 8I. Now let's take a look at powers of I. What is I squared equal to? Well, we know I squared is I times I, and I is root negative 1. So what would root negative 1 times root negative 1 be? It's negative 1. Just remember that I squared is equal to negative 1. We're going to use that in future problems. Let's simplify I cubed. Well, I cubed is I squared times I, because when you multiply common bases, you add the exponents. You remember that from Algebra 1. Now we just saw that I squared is equal to negative 1, so it's going to be negative 1 times I, or negative I. What about I to the fourth? Well, that could be broken up into I squared times I squared, or negative 1 times negative 1. So that's positive 1. So remember that every I to the fourth you see is going to be equal to a positive 1. Now let's step it up and look at I to the 21st. Remember, every 4 i's is 1. So if I broke this up into I to the 20th times I to the 1, I to the 20th, all those i's, because every 4 i's is 1, 1 to the 5th is 1, that all just drops out. So all you're left with is I. Let's look at I to the 26th. How many 4's go into 26? 6 4's. So those 6 I to the 4th are all going to drop out, and you're going to be left with I squared, which is equal to negative 1. You're going to notice that I try to have you memorize as little as possible. I don't want you to have to remember 10 rules when you can just get by with 2. Just remember that I squared is negative 1, and every I to the 4th is 1. So looking at I to the 31st, how many 4's go into 31? 7. So I'm going to break this up into I to the 28th times I cubed. Those 7 I to the 4th just drop out, and you're going to get negative I. Number 7, what goes in, how many 4's go into 100? I think 4 goes into 140. So those will all drop out, and then you'll be left with I cubed, which is negative I. This one's really tricky. If you just multiply the radicals like you would normally, you're going to end up getting the square root of 16, which is 4, but it's not 4. If we follow the rules of imaginary numbers, and we take out the negative 1 is I, and we take out the 4 is 2, we get 2I root 2 times I root 2, and then that'd be 2 times I squared times root 2 squared. You actually end up getting negative 4. This is really tricky because negatives that are inside the radical do not follow the same rules as negatives that are outside the radical. You need to treat them like imaginary numbers. Now try these. This would be I root 10 times root 8. That's I root 80. There's a perfect square factor of 16 in there we can take out. So it's 4I root 5. Here we can't just multiply them. We already talked about that. We're going to have to simplify this as I root 6 times I root 3, which will be I squared root 18. I squared is negative 1. We can take a 9 out from the 18, so it's going to be negative 3 root 2. This one would be I root 5 times 2 root 5. So that'll be 2I times root 5 squared. Root 5 squared is 10. No, it's root 25, which is 5. Root 5 times root 5 is 5. So you get 10I. And finally, just a little bit about complex numbers. A complex number is a number that is part real and part imaginary, and it fits the form a plus bi. A will be your real component, and bi will be your imaginary component. All you're doing here is stating whether you think it's a complex number or not. 3 minus 2i, obviously, it's got the real component 3, the imaginary component negative 2i, it's complex. Obviously, the second one is also complex, but is the third one complex? Actually, yes, it is, because it could be written as 0 minus 4i. 0 is the real component, negative 4i is the imaginary component. It's complex. How about number 4? The natural number 16. Is it complex? Yes, because it could be written as 16 minus 0i. It has no imaginary component, so we say it's 0i. It's also complex. So what does that mean? Well, that means that our real number system and our imaginary system put together are actually elements of the complex number system. There are some numbers that are complex that are part real and part imaginary. They go out here. But every real number is complex and every imaginary number is complex.